Welcome back, everyone. Episode 8, and today we're going to create paths. But first, I want to improve our select a tile code. So, as you might remember, last time we implemented the visualization of Dijkstramaps, and you could click a tile, and then the view would show the map in colors. However, the code to select tiles is really kind of janky. So sometimes it sort of works, and sometimes not at all, or it misses the tile and chooses a different one to select. So typically only the ones at the extremes tend to somewhat work. So let's fix this first so we can at least have a reliable way of selecting tiles. So let's go to our touches began function, and we're going to do this a bit different. So this implementation is really naive because what it basically does is it finds the first node that it can match to a certain point in the view. But our tiles overlap because they're drawn from the back to the front. And that means it's more or less random which one gets selected because the nodes at scene point doesn't say anything about the order in which they are returned. So this is really a sort of hit or miss kind of solution. I want to do it differently in that I want to look at, okay, you click somewhere. Let's see, do I still have it open? Let's say you click somewhere. I want the tile to be selected that is where the center of the tile is closest to where you're clicking. So because that's probably the one that you mean. So what I will do is instead of getting this single node, is we'll do it a bit different. So we'll create a list of node coordinates, and this also uses the nodes at scene point function, but we don't just use the first one. We're going to sort these. And we're going to sort them by the position of the tile minus the scene point. So this is a vector from where you click to where the tile is anchored. And we want to see if this one is closer than the other node that we're going to compare to. And we need to compare these by their size. So we could use like the length of the vector or the square magnitude. That's a bit less calculative intensive. So you need a square magnitude. However, the CG points don't know square magnitude as a function. So let's create a quick extension that adds a computed property of type double that just returns. And this is slightly more efficient than taking the actual length of the vector because we didn't have to do a square root. So now the square magnitude we can get, but we still have a problem because we try to subtract 2 points from each other, and that's not something that's directly supported. So we can create a static function in our extension that implements the minus operator that takes 2 CG points, returns a new CG point, and all it does is look at the left hand side of x minus the right hand side of x, left hand side dot y minus the right hand side dot y. So now we should have a list of coordinates nodes sorted by how close they are to where you're clicking. So the one that's nearest gets clicked first. The second step, what I want to do is I want to make sure that we we only look at tiles and not, for instance, the node, the entities yet, and that we get back their position in as a vector 3. So not just the position in screen space, but basically the position in world space. So we do a contact map where we bring in a node and we get back a vector 3D optional. And we do that by seeing if our node user data has the coord property. Only tiles have these, units don't. And we see if this is indeed a vector 3D, or these can be cast as vector 3D, and if not, then we return nil. Otherwise, we return the coordinate. So now, let's see, user data is an optional. Okay. So now we have a list of vector 3s. And finally, what I want to do is I want to filter on the ones that are at the top. And the reason I want to do that is because we don't need to be able to select tiles that are not on the surface of our map, as our map doesn't have any holes and only has elevation. So the way to do is I'm going to filter them out and look at the ones where the coordinates is exactly the top coordinate in our map, including the elevation. And this does require a quick change because here, when going until elevation, we should also include the elevation. This way we can get matches here. And now finally we can get rid of this code. And we can say if let click tile equals our node coordinates at first. So that should be the closest one. Then we set our selected coordinate to our click tile xy value, because this one is a 3D one and this is a 2D one. So let's see if this works. So we should now have way better selection than we used to. So this is looking a lot better. The only difference is that we now have 2 layers of bottom because our height map starts drawing from 0 up until the end, and including the elevation, and our height map has 1 at the lowest. You could fix this by making sure that either your height map starts at 0, or you can choose to only go from 1 up. Also, I still noticed one thing: our sprites are not aligned correctly anymore. That's because we're drawing an extra roll. What we should do is change the anchor point to offset them correctly, and now they're nice and still on top of the world. So I think this is an improvement in the way we select, and this is something we can reuse going forward. Now let's look at paths. So to do that, let's open a ASCII flow. And this is the way we're going to do path finding. So let's say we have a height map here. This is our example height map, and we want to know the shortest path from coordinate 3, 1, that's this one, to here. Now basically what Dijkstra says is then you need to go roll down the hill. So it's like water choosing the shortest or the easiest path down. So to do that, we convert our height map into a Dijkstra map, and this is still coordinate 3, 1 and coordinate 0, 0. And we use the starting position as the target from the Dijkstra map. That's where we start building it up from, moving it up from. And with this starting point, we see we have a cost of 6 to get here. What we now do is we start at this coordinate and start rolling down the hill. Get this all on the view, otherwise I need to zoom out a bit. Okay. So we construct the path by starting at the target location, that's here, and subsequently choosing the neighbor with the lowest cost as the next one. So we look at all the neighbors here on west, south, east, north, and we see the north one has the lowest cost. So let's choose this one as the next one. And then we do the same thing. We look at all the neighbors and choose the one with the lowest cost. That's this one. And then same there again, this one, until we finally reach the intended location. So we get a sort of path, but I call it path accent because if we write it down, it's actually the reverse of the path we need. So to get our actual path, we simply need to reverse this list, and then we get our final path. So that's what we want to get out of this. So this is what we need to implement. And we can start by writing a test that validates indeed this path creation code. So let's go create sorry, a test for a new getPath function for our example map. And what we want to do is we get a path from 0, 0 to 3, 1. So we need a map. And then we create a Dijkstramap with the starting location as target. So the Dijkstra is map Dijkstra for 0, 0. Then we get the path from 0 to 0 to 3.1 using the Dijkstramap. So we create a path, and the path will come from a function called getPath. This function will take in a target, and this will be our vector 2D 3, 1. And we will use a Dijkstra map. I'm passing in the Dijkstra map deliberately instead of creating it on the fly using the path function, because I want to be able to reuse Dijkstramaps if possible or if needed. Then we get an expected path, and that starts at 0, 0. Basically, what we can do is we can take this one. This is an array of tuples, and we can map this one to an array of vector 2Ds. So now we have here an expected path as an array of vector 2Ds, and then we can assert that the path we get back is the same as the expected path. So let's implement a step for our getPath function. So let's open a second editor, go to our map, and create a new function that goes to a coordinate called of type vector 2D using a Dijkstra map. And this is a dictionary from vector 2Ds to integers for the costs, and this returns an array of vector 2Ds. And for now, let's just return an empty array. So let's see if this now builds and at least compiles. Let's run the tests. Okay, so our test fails because we get an array back and we expect an array with 4 vectors in it. So let's start implementing this function. So let's create our path, and the path will always include the end position, and the result will be path.reversed, as we said, because we're creating an inverse path first. So that's where we start. Then we create a variable called current. This is the current coordinate we're looking at, and we start at the end coordinate. And then we continue by evaluating our Dijkstra map for the current coordinates, while this one is still not 0. Then we take the neighbors of our current position, and we change the current position to our neighbors, the one with the lowest Dijkstra map value. And we do that by using the minus function and then taking the Dijkstra map, taking in the first coordinate to compare with the default of int max. This means that if the value is not in the Dijkstramaps, we assume that it has an extremely high cost and should be not be used, and the same for the other one to compare to. So basically, this is doing a sort of sort and then takes the lowest one. Okay, let's see. Current, I have which one is an optional? Let's just check. Coordinates on the Dijkstra map. Neighbors current. Oh, wait a sec. This one we need to force unwrap because this always should always work. And as we are already checking that we're not at the end location, then we append the current value and the current node to our path, and then continue. And once we reach where the current value, the cost at the current tile is 0, then we have our starting location. Then we can return our path, but then inverted. So let's quickly test this one. And we see it now works. Okay, there is one tricky bug in this code, and I'll demonstrate using a test. So if we do our get path function, we should have get back an empty path if the target location is not on the map. So if you want to go somewhere that's basically unreachable. So let's create our map. Let's create our Dijkstra map. For instance, from 0, this doesn't matter. Then we create a path. We do a get path to a vector xy, say at 6, 9. This doesn't exist, using our Dijkstra map. And we want to assert that the path is an empty array. So let's run this test. So the test starts, and it runs, and it runs, and it runs, and let's pause it for a sec. Let's step out and see where we are. So we're at this step. What we already can see is that if we continue, Our path already has a billion values. Basically, this thing is stuck in an endless loop. What we need to make sure is that we check whether the Dijkstra map keys contains our coordinates. Let's go back to this one. Contains our coordinates, else we return an empty array. Let's run the test again. And now the test passes. Okay, cool. So we can create paths. Let's make sure we can show the path on the screen. So let's go back to our game scene, and we can get rid of this one now. Let's go all the way up. We here keep a Dijkstra map. We'll create a quick path array. We can show the path. Then instead of what we're doing here, we still need a Dijkstra map. And let's say we start from a position 1, 1. That's where one of the knights is, so that looks a bit better. And what we do is we create a path to our selected coordinates using the Dijkstra map. And if we don't have a selected time, we just take our path and remove all entries, so we don't show any. Then instead of this code, color code and distance code based on the Dijkstra map, we simply check if the path contains the position. Then we color the path bluish, so we color the tiles blue. And if we run this, we should be able to click tiles, and we will see paths shown on the screen. So let's click here. We can see a path from 1, 1 to this position, or this position, or this position. Notice that it now chooses a different path because this one apparently is cheaper. Let's go here. It takes the one with the least, that's basically flat. See how it does this one? So it's still easier to just jump up instead of going the long way around. So this is how paths are now determined. One thing I do want to do is I don't want to color these in between ones because you don't really hit these. I only want to show the top one, so what I'll do is I'll make sure that our Z value is the same as the elevation value, so only the top one gets shown, and then if you choose this one, we just get a path that shows indeed that there's a jump here. So that's creating paths and showing a path. And next time, I want to make sure that we can, let's show it again, that we can actually have a unit follow a path. So we'll say there is a path, and then we will make sure that the unit is able to follow the path, that it's animated, that I'm not sure whether we can do it in one episode with also changing orientation to the correct place. But that's what we're going to do next. I want to be able to have units follow paths. So thanks for watching and have a good day.